Hey everyone, Morgan here. So we're going to be talking about some bonding and Lewis structure stuff again today. And we're going to be working on pages 4 and 5 of the lecture outline. So we have what is considered kind of a tough concept here. And it's the idea of resonance. Now the definition says a condition occurring when more than one valid Lewis structure can be written for a compound. Now, that does not mean the compound exists in more than one structure. It just means we can write more than one valid Lewis structure for it. And we're going to talk about what happens with that. So let's begin with the nitrate ion. 5 valence electrons for the nitrogen, 6 for the oxygen, an extra one because of the minus sign. Now, I'm going to do these as line structures. Makes it a little bit easier to see what's going on. I can do a double bonded oxygen that's got 2 lone pairs, a single bonded oxygen, a single bonded oxygen, and that structure is good. 3 times 6 is 18, plus 5 is 23, and the extra one is 24. So that's 12 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, because it's an ion, I'm going to put some brackets around it, put a minus sign there. Now, the octet rule is satisfied for all atoms, which is good because nitrogen and oxygen pretty much obey it. Okay? And the structure looks great. And if you put that on a test, you're very likely to get it marked correct. However, we have the double bond here. Could we draw it with a double bond there? The answer is yes, we could draw it that way. And there's another acceptable Lewis structure. We can even put in one where the double bond is pointed off in that direction. Now, all 3 of these are valid, acceptable Lewis structures. So the question becomes, which one is correct? How does it actually exist in nature? Well, it doesn't exist as any of these. It turns out that when we measure the bond energy and bond length for these 3 bonds, they come out to be identical, not a double and 2 singles. And the energy is the equivalent of about 1 1/3 of a bond. So what that's telling us is that the electron density that you see in this double bond that's right here gets spread out evenly over all 3 sites. Okay? So it's shared electron density that has been evenly distributed. Okay? Now, we tend to use the term delocalized. Okay, that electron density has been delocalized. It's shared over all 3 of those sites. Now, I have seen somebody explain this by actually cutting a bagel in half and taking what is, cream cheese or jelly or whatever you want to think about it, and putting 2 stripes here, a stripe here and a stripe there, all on the bagel. And then with a knife, spreading it out evenly over all 3 spaces. That's what's happening to the electron density. Now, for NO2 minus, we can do a double bond on the left, a lone pair, and a single bond on the right. we can also do a double bond on the right, a lone pair, and a single bond on the left. And what happens here is that we say the electron density delocalizes over both those sites, and you have two identical bonds with a bond order of about 1.5 or 1.5. Okay? So, these are correct Lewis structures. All of them. What does the polyatomic ion exist as in nature? Well, it exists as one structure with the electrons delocalized. Now, XeO3, that's an interesting challenge. On the AP exam, even, they let you get away with this. All single bonds, they happen to be coordinate covalent bonds. 3 lone pairs on each of the oxygens. Okay, I'm sorry. Get rid of that one. There we go. Now, that's going to be a lone pair. That's great. But we can also have Xe double bond O with a single bond O, single bond O, and a lone pair. That's possible too. And if you keep going like this, it turns out there's about 8 total structures that you can draw. Okay? Not all of them are the way it's going to exist in nature. Okay? If you want to look in chapter 8 of the Zoomdahl textbook, they actually do a nice big example about this exact compound. Okay, moving on to page number 5. We're going to be talking about isomers here. Okay? Now, iso is a prefix we know means equal or the same or something along those lines. So what we have here are 2 distinctly different compounds with the same chemical formula. Or we could also say 2 distinctly different structures with the same chemical formula. Now, C2H2Cl2. I think the best way to approach this is actually with models so that you kind of get a feel for what's going on. So here is one possibility for this. C2H2Cl2, it has a double bond. The white ones can represent the hydrogens and the green ones can represent the chlorines. Now this molecule, can't twist because of the double bond. So what we have to say here is that these green ones are across from each other. However, I can also show it to you where those green ones are on the same side as each other, and I can't twist it to turn it into the other one. I can even show it to you where the green ones are both on the same carbon and not on opposite carbons. All 3 of these represent isomers of that formula, and there are also some different types of isomers. So we can draw this as a line structure with the hydrogens on the same side, chlorines on opposite sides, or we can draw this, again we'll use line structures here, with the chlorines on opposite sides of each other, or even where the chlorines move which carbon they're on. Now, we have some names for this. This one right here, where the chlorines are on the same side, we call a cis structure, and where they're on opposite sides, we call it a trans structure. So these are what we might refer to as geometric isomers, where we are just changing the 3-dimensional positioning of the atoms. Whereas this, I was taught, is a positional isomer. because we have changed the position of the chlorines. They're on a different carbon this time. Okay? Older folks tend to call these constitutional isomers. You're not going to hear that very often anymore. Okay? All right. So, free radicals. These are species that have one unpaired electron. These are generally considered to be very dangerous, okay, very reactive, and not something you want to deal with. Now, the No2 molecule is a great example of it. Nitrogen, I'm going to do line structures, double bond to an oxygen that has 2 lone pairs, single bond to an oxygen that has 3 lone pairs, and 1 leftover electron. 6 plus 6 plus 5. Okay, that's 17. 2, 4, 6, 8, 10, 11, 12. I'm sorry. 2, 4, 6, 8, 10, 12, 14, 16. And there's 17. Okay? Now, there's nothing you can do to get them all paired because there's an odd number of electrons there. But what tends to happen is called dimerization, di-2-mer molecule. So this one is very likely to pair off with another of the same molecule. And those 2 lone electrons can form a bond, and this would be referred to as a dimer. Now this is smog, okay? And this N2O4 is not, okay, dinitrogen tetroxide. Now it turns out that at higher temperatures this breaks down into this. And that's why smog is worse in the summer hot months than in the winter when it's cooler, because more of these come together and don't break apart. Okay. Now, Lewis acids and bases we talked about in the first couple weeks of school. I'm just going to refer to them because it is the idea of a chemical behavior based on structure. So an acid, in the Lewis definition, is an electron pair acceptor. And a base would be an electron pair donor. So let's see how that works. I love the reaction of BCl3, boron trichloride. We'll do the lone pairs as line structure. And ammonia. Now we know ammonia is a base. And what can happen is this lone pair can come over here to where the boron does not have an octet. And what we can end up getting is a boron bonded to a nitrogen, which has 3 hydrogens coming off of it, and the boron has the 3 chlorines coming off of it. Okay. All right, so those are 4 very different ideas: resonance, isomers, free radicals, and Lewis acids and bases. That there's no real specific way we should put them in any order or anything, so I just kind of threw them all in there over those 2 pages. Okay, there will be questions about this that you're going to have to deal with in your next test, so make sure to spend some time on these. Okay, this is Morgan signing off.